Hi, in this research we present how to improve the performance of neural codecs by using already existed gradient of the entropy in decoder side. I am Muhammet and this is joint work with Bharath, Karam, Frank and Pierre from Interdigital France. Current state-of-the-art neural image codecs uses two stages hierarchical variation autoencoder. The model consists of 5 trainable blocks given in green in the figure with their inputs and outputs. The second stage of VIE encodes the side information, where the first stage encodes the main information. Here, side information defines the distribution of the main information, and the main information is for reconstruction. The loss function can be defined by the sum of main and side information bit length as well as the reconstruction error. Thus, the optimal parameter, trainable parameter, can be found by minimizing the loss function over train set. However, the main and side latent obtained by learned parameter are highly likely not optimal for a given test image. These latent representations can be fine-tuned before encoding to the bit stream. We call these solutions as fine-tuning solution, which can have 5 to the 15% coding gain in exchange of encoding complexity. During decoding, first side latent should be decoded from bit stream using shared factorized entropy model. Later, using hyperprior decoder, we can obtain the entropy model of the main information shown by mu and sigma. Using this entropy model's parameter, we can decode main latent from bit stream. In the final step, we can use deep decoder network and obtain reconstruction. Here we are looking for adding something to the latent which decreases the error. For sure, we need to take a step of negative direction of gradient of the error to decrease the error. However, gradient of the error cannot be known by decoder. On the other hand, the decoder knows gradient of the side and main entropy. Because these entropy models are available, our contribution is to show that these two gradients are correlated. Thus, we can use available one as it is necessary one in order to decrease error. In order to show some theoretical reason on why these gradients are correlated, let's first call neural codec as unconstrained multi-objective optimization problem. If we define 3 objectives and 3 weights as shown, we can rewrite the loss of the neural codecs in a form of unconstrained multi-objective optimization problem. It is very well known that optimal solution of multi-objective optimization problem should meet KKT condition. In plain word, this remark shows that at the optimal point, all forces driven by gradients cancel each other out and the solution reaches a saddle point. This condition is also valid for neural codecs because they are already unconstrained multi-objective optimization problem. When we take gradient with respect to main information, we reach the second condition in the theorem. This condition tells us the gradient of the main entropy and the gradient of the error with respect to the main latent can cancel themselves out in the expectation of the train set. If these conditions were valid for every single image, a given test image's available gradient would be the opposite of the unavailable gradient. Thus, they would have -1 correlation coefficient. However, these conditions are valid in average on the train set. But we claim that this relationship still holds approximately for any single test images. According to our test on several neural codecs, we found quite a strong correlation between gradients as it is shown on histogram in the figure. Now let's define how to use these correlated gradients in the compression pipeline. During the encoding, the best step size that minimizes the error if the latent shifted by gradient of the entropy should be found. Later, this step size should be added to the bit stream. In decoder side, first, this step size should be read. Later, gradient of the entropy can be calculated. Main latent should be shifted by a step size of gradient of the entropy. Finally, shifted latent can be used in decoder network in order to get reconstruction. In the table, we can see the BD rate performance of Latent-Shift on 5 different on-the-shelf neural codecs on 2 different image datasets. Our method saves significant amount of bits. In order to show complexity, we conduct further tests with and without fine-tuning solution in Table 2. Here we show also how Latent-Shift can save more bit after fine-tuning solution. For more information, please check the paper and also don't hesitate to contact us. Thanks for your attention.